So I wanted to bring us back down to the subsurface, thinking about characterization and siting. And as Tara mentioned, we're kind of in the very initial part of this work, and so we don't have the detailed kind of conclusions that you've seen from these other reports. So I'm sorry about that, but the benefit of that is that it's not too late, that we can get some recommendations from the audience, and so we're really open for suggestions, comments. This is like really the early stage, so just want to make that clear. And so I'll just introduce our team a little bit. Chanmali Chun, Molly, recently joined us from Japan, so she's worked on a number of geothermal and potential superhot resources in Japan, as well as New Zealand and Kenya. And her expertise is mostly in seismic methods, but also kind of bringing in a bunch of different methods, which is going to be a big part of this report. My background is more in rock physics and rock mechanics from the laboratory scale. So how do we use lab experiments to interpret the geophysical signatures that we're going to be talking about? We're lucky that Rebecca, who you heard from earlier, is going to be helping us out from Cascade Institute, and she's kind of has more of an electromagnetic background. So we try to kind of cover a lot of the geophysics methods that we're going to be reporting on. But as I said, we're just starting this research, so the type of preliminary gaps that I've identified are really just coming from our experience. They're not from a kind of a thorough analysis quite yet. And so I'd like to thank Tara and Clean Air Task Force for getting us involved in these reports. The Cascade Institute is supporting Rebecca, and we're supported by the Cornell Atkinson Center for Stability. It has a lot of the same goals that Tara mentioned for Clean Air Task Force. And so again, I'm bringing us back down to the subsurface. If you think about that figure that I like how Trenton put it, you have this kind of cartoon of your wells going down. Something is happening down there. That's where you're creating your permeability. He at least had some layers, but often these are very simplified views of what is in the subsurface. So our report is sort of what are the methods and how do we get at kind of filling in that gap? What is at least a conceptual model of what the geological reservoir is and what the setting is? So to kind of capture that scope, we're going to cover a bunch of different geophysical techniques that are sort of figured up here abstractly. So these are the seismic methods, electromagnetic methods, gravity, magnetic, geodesy. So I'm going to kind of go through these quickly. These are the things that we're going to kind of want to understand what they can benefit for, what they can bring to us. But maybe more importantly in this report is how do all of this type of information get integrated, and how do we iteratively improve our model of what is going on in the subsurface. So important in this, and it's been mentioned a little bit, is well hogging tools. This is kind of like our ground truthing of what the geophysical data is how we're interpreting the geophysical data. And then how do we use machine AI-related data assimilation, joint inversion, all of this sort of methods to understand how do we integrate different types of geophysical information, what is the value of each of them, how do we decide what's the most important to capture, play fairway analysis in terms of understanding where we should locate those wells in the first place, what are the hazards that we might have to take into consideration, how deep will we have to go to get to the temperatures that we want. I mentioned briefly like laboratory type of experience for understanding how do we best interpret the data that we're looking at. And then looking forward, we have a baseline idea of what the subsurface looks like as we do our engineering changes, we enhance our reservoir. How do we continue to monitor and understand and target the actions that we need to take down there? So that's just the life cycle analysis. So just very briefly, kind of everybody is somewhat familiar. Where are the geothermal resources? Where settings? We're thinking about, again, kind of our initial demonstrations are likely to locate in places where we can get to super hot temperatures relatively shallow. So these are going to be subduction zone settings, thinking about volcanic settings in New Zealand, Japan, Indonesia, Philippines, Cascades, or more extensional settings, East African Rift Zone, here on the mid-ocean ridge, the basin range, areas where we can get to heat relatively shallow. But again, as we've been talking about, we want to move forward to being able to go deep enough. If you go deep enough, you'll find the temperature. So that's a different type of geodynamic setting that you're going to have to take into consideration as you start the process of characterizing your resource. I think we've seen this figure before. These are the areas that have already kind of been located supercritical resources, often referred to, talking about going to the roots of a geothermal system. And so there are some nice examples and data out there, but there still is really one of the gaps I think we'll come to is that there's a limited number of places where we have actual information from the well to tie down to our geophysical data. People in the academic sphere have worked a lot on geophysical imaging of magma chambers, and there's a different level of comfortability with uncertainty in that community. We really want to be able to confirm what our interpretations are. So I think the only way really to move forward is what we've been talking about, drilling and iteratively improving our models. So what are the kinds of structures and things that we're going to be looking for? I think it comes down to, it's been brought up, looking at locations where you imagine even if there's not fluids, there's fractures or places where we can increase our permeability most easily. And so these are kind of anomalous areas. I'll go through the more specifics, but the seismic velocity, resistivity, density, all of these are telling us different properties of the rock that when you see an anomaly, it's going to point you towards some structure that may be either a source of hazard. You don't want to go into a magma chamber, or you might not want to go into an active fault, but you need to know what those structures are in both a positive and a negative respect. And so the way we see this project is we're kind of going through the site selection process. This characterization is part of the entire development scheme. So from the exploration scale, in terms of understanding where it is you want to site your drilling, a big part of this is just kind of improving our odds in drilling what we're going to find down there. So we want to decrease the costs associated with drilling by knowing what you're going to find. And so this starts at a larger scale and then slowly moves down, and you get more and more detailed information as you get down to the scale of your reservoir. And then as you get wells, you start to get really detailed meters, tens of meter scale information about, okay, what is the depth at which you're going to undertake your enhanced permeability enhancement. And then I think I mentioned quickly, so you have some baseline model of your subsurface. These methods are particularly good at giving you relative properties. So as you make changes in the subsurface, looking at the time dependence of the properties, that's where you're going to get the best resolution. So you have to have a really good model to start with to know where you're targeting, but then you have to iteratively compare your measurements back to that model, and that's the monitoring aspect through the life cycle. Okay, so yeah, now I'm just going to kind of go through quickly again. What are these different technologies we're looking at? What are the types of things they're measuring? And what are the shortcomings? What are the things that we're going to focus on and try to improve our information? So at the large scale, we have these global or regional, continental scale heat flow maps. This is an example of a map of the magnetic Curie depth. So if you, by measuring magnetism at depth, there's a temperature at which the poles, the direction of the magnetic field is lost, right? You go down into it. So we have this measurement of what that depth is. And as you look around, places where it's shallower are going to have higher heat flow, a larger geothermal gradient. But this is kind of a large scale, that's faster, sorry, measurement, and so it's not going to be really sensitive to the small scale features that we need. I'm going to go through a little faster, I didn't realize. Another type of larger scale data, you get surface information from geodesy, for example. So if you're in an area of active magnetism, then you may see surface uplift subsidence. Depending on what's happening under the ground, you might see active deformation. So this is a way to kind of identify those hazards. And also sort of the stress regime that you're in. Another way to understand the stress regime that you're in is looking at seismicity, microseismicity perhaps. talked about induced seismicity as something to avoid, but microseismicity also is a really important source of data, of information we have. So looking at the focal mechanisms of your earthquakes, the location of your earthquakes gives a sense of the structure and what the stress regime that you're in. But that being able to locate earthquakes accurately, you need a really good velocity model, so how the seismic waves travel through the subsurface at different speeds in different locations. That's also, this tomography of seismic velocities is going to give you information about the temperature structure, where the fluids are. Anisotropy in the seismic velocities is going to help with structure. And then reflection will help understanding structure and faults. Similarly, you can get a 3D model from the density, from gravity measurements, or electromagnetic measurements. And so by making measurements for your elasticity, your seismic properties, your density, your conductivity, these are all kind of sensitive to different aspects of the subsurface, but they may give you similar ideas of what structure there is, and how they relate to each other, how you can jointly interpret them will be giving you a lot more information about what you expect down there. Also, sometimes you might, one type of data is going to suggest one thing, and that may be not consistent with what another type of data is. So in the end, you need to be able to kind of ground truth this. So once we have wells there, we got logs, we can actually tell in more detail at depth what is the properties that are going on to refine our geologic models. If you can get core from those wells, then you can do lab experiments on the core to better interpret what the seismic data, the geophysical data you have. For example, here, like if you change temperature in the lab and look at how that affects your seismic velocity, then you can see at these super hot, kind of supercritical conditions, we expect really drastic changes in the mechanical properties should be visible in the geophysical properties that we're measuring. And then again, how do we jointly invert or jointly interpret these different disparate data sets? The properties that you're getting from your geophysical model will then be input into your reservoir models. Iteratively, you can, as we were mentioning, you can get better and better idea of what your subsurface properties are. And then we can use this machine learning, other data assimilation type methods to integrate all the different types of models and see, have a kind of a baseline geological conceptual model. And so one thing that's come up already in our initial scoping is that really that it's important to have sort of a standardized characterization approach here, that there's really a range of different expertise and types of data here. And so if we were able to come up with some recommendations of like, okay, the value information, what are the things that you really need to have, and how, at what scale you can expect, what are the types of interpretations in these sort of geological environments, that will be valuable for getting these projects off the ground and up and running. And so just to end, since again we haven't really totally done this research, we're starting a literature review, but we plan to also kind of identify these locations and these projects that have been active and that have done a lot of this, and kind of uncover through interviews, through reaching out, what are the common challenges, what are the advantages and difficulties in different sites. A lot of things don't actually get published necessarily, or are not so easily available. We have to really identify where the data is available, how to reach it, how people can learn from it, and these lessons learned, and what are the future plans. So maybe I sped up too fast, but I think that was where I wanted to go.
As we indicated in the beginning, the intent of sharing this here was to take in your feedback. So I do want to open it up for Q&A, but also understanding that he had to speak very quickly, we will make these slides available on our website so you guys can peruse them. And also, please reach out to us. Different than the other reports, this one will have a small board of advisors so that we can be pulling from learnings like those that happened during Deepen, et cetera, and continuing to feed this. We don't want to start from the beginning. There's a lot of literature on this. So we'll take questions for 5 minutes or less. Anyone?
Yeah, John Ludden. Yeah, I want to follow up a little bit on your last point on data, right? Because I thoroughly agree with you that actually having all the data in one place is fundamental. Yeah. So if you take Europe, there's a project called EPOS where we try and do that, right? You might have heard of that. But actually it tends to be very academic data. And so what needs to be done by a group such as this is to actually extract the more applied aspects of that academic data to geothermal exploration. And if this project can do that globally, that would be very useful in a couple of key pilot sites.
Yeah, no, definitely agree. I mean, I don't have so much to add. I know that in the U.S., like if you're publicly funded in some way by the DOE, you have to go to the Geothermal Data Repository, GDR. So there's a lot of data there. It's not always the most accessible, also. So yeah, I think this is a big issue that needs to be addressed. Yeah.
That's another question, Susan.
So a lot of the play fairway analysis was developed for hydrothermal resources. And so as we start to adapt those methods to EGS, what additional information are we going to want to get? And how is that going to fit in with our analysis of the favorability of the sites for their site selection?
Yeah, I mean, I think it'll change dramatically. So the play fairway analysis, like you said, in conventional sites, it's all about where's the heat and where's the fluids. So we're kind of changing half of the equation there, in not necessarily needing the fluids to be there. So that's not something we haven't kind of gotten there yet, but I think that'll be a key part of looking at these sites, of the siting part of it, the play fairway analysis. Yeah.
Any others? Of course, the back.
Thank you, Seth. Speaking as a geophysicist, I would really sort of like to ask, because we talk about Superhot within where we have volcanoes, but we also want to go to other places. So I think it would be interesting to see or do an analysis to see what data sets are the most important ones in different settings, because yeah. I mean, like we say, we know where the Superhot is within volcanoes. You know, there's something down there. But if you go to other places like cratons, or then I guess other different geophysical methods are going to be the most important. So at least for me, I would like to see something like this, like categorized.
Yeah.
Just a comment.
Yeah, I see it's sort of a hierarchy. So when you start the first place you start is sort of the geodynamic setting, and then you'll follow a different trend depending on what your base expectations are. Right? So that's a great suggestion. Thank you.
Any others?
Trenton had a question up here.
Trenton, yell out.
Yeah, maybe I could just repeat it.
Well, it's related to that, which is temperature depth maps. There's been a lot of them, like the Basin Range. There's 3 new ones now, and they're all very different. It's actually kind of scary to me is hitting 450 at one map was 15 kilometers, one was 10, and there's a big variation. So just depending on model inputs, but I guess that's just, I don't know if that's a question.
Yeah, it's an important point. Exactly. I guess everybody heard that probably, but yeah, that I mean that's something that we see is like between methods, even different methods that take in the same types of data potentially can come to different conclusions. And so I think that's what comes down to is like there's a little bit too much uncertainty in just the geophysical picture, and that's why we need to do some ground truthing. And I think iterating through the ground truthing and the geophysics is going to be key to having more confidence.
Having just wrapped up our own modeling, intended dominantly to just demonstrate abundance of the resource, but we did come across that exact question. And by focusing on the conductive versus the convective flow, the anomalies were wild and questionable. And so I think that having a concerted effort to mesh the various ways and identify, perhaps even to Astis's point, in which tectonic domains or which types of lithologies are we seeing more accuracy than in others using different methodologies.